So good morning, everybody. So resuming the lectures on black hole gastrophysics from where we stopped yesterday. Let's continue talking about the basic concepts of GR and remind you about what black holes are. And for this purpose, I wanted to just, since I spent time writing this little app here, Mathematica, that explores light cones, the behavior of light cones in the Schwarzschild spacetime, I might as well and show you what happens with light cones. So here is, if anybody wants this this little Mathematica notebook. By the way, who uses Mathematica here? Can you raise your hands? Almost, let's say half, perhaps 2/3, a lot of people. Who uses Jupyter notebooks? Can you raise your hands? Comparable. There seems to be an overlap, significant overlap. Right. So if you are interested in this notebook, I can give you, I can share. Let me execute this. Let's see, evaluate. So what I'm doing here is I'm taking some appropriate coordinates. And I hope I will write Schwarzschild correctly. Is this correct? Is it? Okay. As you know, if you write the Schwarzschild geometry, this is the geometry of the spherically symmetric object, and you use Schwarzschild coordinates, the Schwarzschild coordinates, they are not very good because they have coordinates because they have coordinate singularity. So the coordinates, they fail and they give you garbage results at the horizon. So what you have to do instead is you have to do, one suggestion is to use these coordinates called Eddington-Finkelstein coordinates. Nothing fancy here, no dynamic, no numerical relativity here, just a static space-time. So if you use these coordinates, you can write the line element for these coordinates, which I will not remember, but you replace time, the Schwarzschild time, by some Eddington-Finkelstein time, which I will call V, and then this is the only change basically, so R, theta and phi, they remain the same. And here what I will show you is you want to understand what happens with radial light rays, okay? So radial light rays, what you do is then you set the theta 0, the phi 0, okay? And since it's a light ray, you have to so you do these extra requirements here, and then, okay, you specified a light ray, a radial light ray, and then you solve the resulting equation, and then you will have the equation of radial light rays in Schwarzschild spacetime. And then you can plot what will happen with the light cones, and that's what I've done here. Let's see which one of these. Yeah, that's the one. Oops. Okay, so the blue line corresponds to a radial light ray, which is trying to escape the black hole. Okay, so the light, like, look, I want to go, I don't want to fall, I don't want to die, no. That's the blue light ray. And the orange light ray is, imagine you have a flashlight and you are falling towards the black hole. well, that's a static event. But imagine you are falling in a black hole and you have a flashlight and you're throwing one light ray away and one light ray towards the black hole. So this is a space-time diagram. Our conventional R coordinate, that's basically time. Okay, it's a coordinates a proxy of time. So the coordinates were chosen such that they look like the traditional light cones of special relativity with the 45 degrees when you are far away from the source of curvature. Okay, so these are the light cones, the equation, the motion of light rays, and then this little app here, you can move your observer firing light rays. So this is the Schwarzschild radius. This is the realm inside the heart of the heart of darkness of the black hole. And what happens is, as you move your flashlight, look at what happens with the light cones. Okay, you start approaching your observer firing light rays from the flashlight. Okay, look at what happens with the light ray, the blue light ray, as you approach the Schwarzschild radius. Okay, it starts moving towards a vertical line. Okay, what that really means is that it gets harder and harder and harder for the light ray to escape the gravity of the central object. Please ignore the other null geodesics that will appear here. It doesn't have a physical meaning for the purposes of this lecture, okay? So just ignore this strange thing that is showing up there for the moment. So as the observer is touching the Schwarzschild radius, it gets really, really hard for the light ray to escape the gravity of the central object, but it still can escape, okay? But once you touch the Schwarzschild radius, something funny happens, okay? What happens is that you will have stationary light rays. The light rays, they will get stuck at your horizon. In fact, the surface that corresponds to the is a null surface generated by, let's say, stationary light rays at the event horizon, okay? It's generated by the light rays that get stuck at the Schwarzschild radius. But then fun things happen across the event horizon, okay? Please ignore this strange thing here. I was not able to get rid of this other thing. So what happens once you cross the event horizon, okay, you can still use the physics, nothing, as you know, nothing crazy happens inside the event horizon. But the thing is, your light rays are not able anymore to escape the Schwarzschild radius, okay? And once you cross the event horizon, the central physical singularity at r equals 0 is not anymore a point in space-time, but it will be a point in your time. Because at some point in the future, it will be forced to cross the physical singularity. And I hope that before you cross the Schwarzschild radius, you sign, you tell who will stay with your money once you cross the event horizon in this not so nice trip, okay? So again, this is what the event horizon is, separating these two regions of space-time. And once you cross inside, well, you cannot come back, you can only cross it once. So if you fall towards the event horizon and then you cross the event horizon, nothing special will happen with you. You will reach the physical singularity in a finite proper time in your clock. By the way, suppose you have a black hole with a mass, solar mass, okay? And suppose you are a very courageous explorer and you cross the event horizon. This black hole, we are not sure, probably this kind of black hole is not, you can form this kind of black hole in nature, okay? This is a kind of astrophysical black hole because there will be some kind of pressure that will be able to support gravitational collapse for this kind of low masses. But suppose you cross the event horizon of such a small size black hole, okay? And then you will be forced to collapse to the physical singularity at r equals 0. Do you have fast it will fall towards the physical singularity according to the proper time measured in your clock. How long will it take to fall once you cross the event horizon, okay? I will give you a couple of options of here. 10 seconds, 1 second, and let's see, why not? Why not? Okay, so who thinks that it will take 1 minute to fall? Can you raise your hands? In the frame of observer falling towards the central singularity, once you cross the event horizon, in your frame, frame. How long will it take? You think it's 1 minute, right, Fabio? No? Nobody thinks it's 1 minute? Some of you probably did this calculation as part of GR course, but it's fun to remind you. 10 seconds. 1 solar mass. The Schwarzschild radius is it's 1.5. Sorry, 1.5 kilometer. Yeah. Huh? Okay, so 10 seconds. Who thinks 10 seconds? Nobody? 1 second? Nobody? 0.01 seconds. Everybody's sleeping probably. Okay. So let's see. 10 to the minus 5 seconds. Why not? One hand. Okay. So guys, it will take 10 to the minus 5 seconds for you to fall once you cross the event horizon to reach the central singularity, okay? 10 to the minus 5 seconds. If it's a 1 million solar masses black hole, it will take you about 1 second, okay? If it's 100 million solar masses, it will take you, a couple of minutes to fall towards the central singularity. Okay, so gravity is strong, okay? These guys are very, things happen fast. It is supposed to be the back of the envelope calculation. What I'm telling you can do this calculation using the static spacetime, okay? So the back of the envelope calculation is trivial, but the fun thing is doing the actual calculation of the proper time to reach the singularity. Anyway, so if you are an observer sitting outside the black hole, okay, once a star collapses towards the black hole, all records of the star history will be erased for an external observer, okay? And everything will be reduced to 1 or 2 numbers depending on the angular momentum, the mass, and the spin, according to an external observer, once the star crosses its event horizon. So what is a black hole? A black hole is a remarkable prediction of relativity, in the sense that it has such speed that not even light can escape from its gravitational attraction. And so you have this horizon, and at the center you have the physical singularity. The event is a one-way membrane, so matter energy can fall in, but it can never get out, at least with classical processes. The Schwarzschild is about 3 kilometers for if you could form solar mass black nature. Okay, so if you take a bomb with a timer, a bomb of 100 megatons, and you throw inside a black hole, okay, it explodes inside a black hole, but you will never see the explosion happening because the light get trapped inside the event horizon, and the event horizon will grow a little bit. The area of the black hole will grow a little bit once it accretes because its area increases a little bit. Then you take other things, not necessarily very pleasant, and then you throw inside the black hole, its area grows a little bit more. Then you take further unpleasant things, and you throw inside the black hole, and in this case, it grows really a lot, and unpleasant things, and it keeps growing, okay? So the mass of the black hole will always increase when you are classical things to the event horizon, classical processes. For you to have an idea of how compact black holes are compared to other kinds of objects, this is a simple diagram comparing the size of the event to the size of a comparable to the size of a typical white dwarf, to the size of a neutron star, then a black hole. All of them with the mass shown in. Black holes are the most compact objects that nature can form, and therefore they have the most extreme gravity. Having this school in these 3 weeks. I think I can skip these generic features of gravitational collapse. So as I said, if you keep feeding a black hole with particles, the mass of the black hole gradually increase. Its radius will gradually increase because the mass is increasing, the surface area will increase. So in principle, there is no limit to how big the mass of a black hole is, okay, in principle. If the universe wants to keep feeding the black hole will be happy. It will not give you anything. It might give you some things in return, but it will happily grow as you keep feeding the black hole. So we have measurements of the mass of black holes in nature. So it seems like the smallest weight, the smallest mass that we measure for a black hole in nature in a stellar mass, in a system called X-ray binary, it's around 4 solar masses, okay? And so far, the record-breaking black hole that we measure, we estimated the mass, sits in the center of a distant galaxy with a record-breaking mass. Is this intermittent, this audio? Is it my impression? It's a bit intermittent, right? Okay. Maybe I'm doing something that I shouldn't do here. Okay, can you hear me? My apologies for the intermittence. So as you know, a black hole has no hair. So apparently for dynamical spacetimes, the no-hair theorem is a bit more complicated than I thought, as we learned with Ian Steinhoff. But so all black hole solutions of Einstein's equation, they are completely characterized by the only 3 parameters: the mass, the angular momentum, and the charge. We use, as you might know, we characterized the so-called spin parameter of Kerr black holes between -1 and 1. The no-hair theorem assures that if you try to add extra properties to the event horizon, in other words, if you try to add hair to the event horizon, the black hole will get rid of the hair, keeping the exterior geometry characterized by only these 3 numbers. The 3 numbers lead to different kinds of space-time geometries: the Schwarzschild space-time, the Kerr space-time, and for a charged black hole, the Reisner-Nordstrom space-time. But it seems that if you try to add charge to a black hole, the black hole will very quickly attract opposed charge and nullify its charge, okay? So it seems that in astrophysics, you cannot have black holes with significant amounts of charge because they get discharged very quickly, okay? So people don't really consider charge to be an important parameter for astrophysical black holes, gravitationally significant amounts of charge. So from now on, when we talk about astrophysical black holes, we will only consider mass and spin as the fundamental parameters. So we will have the Schwarzschild black hole solution, the first more or less simple solution of the Einstein's equation for a spherically symmetric geometry around a spherically symmetric object. Okay, it's the simplest black hole. It's relatively easy to handle analytically, of course, depends on what you want to do. Okay. If you try to derive the precession of the perihelion to first order, you will realize it's not that easy to do this calculation, which is supposed to be, it will take you, it will give you, it will be a bit tricky to do that calculation. And then we have the Kerr black holes, okay? Kerr black holes, they are expected to be the norm in the universe for the simple fact that angular momentum conservation, angular momentum cannot really disappear. So if you have a collapsing star with some angular momentum, it is getting smaller, 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 like a ballerina or a bailarino. You know, it's spinning and then you close your arm, you spin faster, angular momentum cannot disappear, okay? And then if you have a spinning star that collapses, you will get a black hole with angular momentum, the Kerr black hole. Of course, deriving the solution was not that easy, the first derivation by Kerr. That's why it took about 50 years after the Schwarzschild solution for him to obtain this. And the interesting thing is that you have an extra degree of freedom, that you have rotational energy, which also distorts the space-time around the black hole, okay? So this gives rise to a very interesting and very rich exterior geometry characterized by the Kerr spacetime. Okay, the expression is a bit more complicated than the expression for the Schwarzschild spacetime. You have it's convenient to write this rho and this delta, and then you have this thing here. And a Kerr black hole you can really understand as a spinning object, okay? It's a spinning space-time. It's a bit more complicated than simply a spinning object, but you can really treat it as a spinning, let's say, ellipsoid. The horizon has the shape of ellipsoid now. You can think as a rotating membrane, which has spin, okay? For the maximal spin, which is here I call J equal 1, the rotational velocity of the horizon is the speed of light. And if you could add angular momentum to a Kerr black hole above the limit of J1, it will break the event horizon, and then you will form a naked singularity. But so far, people have tried to destroy event horizons, and nobody was able to destroy and add overfeed with angular momentum of black hole and reveal the naked singularity with calculations. People are trying, but it's very hard. So you can characterize the spinning event horizon with an angular velocity, with a period, with the velocity at the equator. This is the resulting structure of a Kerr black hole. So you have more than one event horizon, okay? You have the traditional event horizon, but you also have inner event horizons, which are not really relevant here because they are inside the traditional event horizon here, so we don't need to really work with them. So besides the ellipsoidal shape of the event horizon, which is a rugby ball, okay? It looks like a rugby ball. You also have the so-called, I'm using this laser, but it's really working, so I don't know why I'm pressing this. Oh, is it true? Oh, wow. Thank you. So, yes, great. So then, besides the ergosphere, okay, so the ergosphere is a region close to the event horizon where you cannot have static observers, okay? So if you approach the black hole and then you get inside the ergosphere, what is happening here is that the black hole is dragging the space, the spinning black hole is dragging space around with it, okay? So if you get close, if you get in the ergosphere, it will be forced to co-rotate the black hole because space is being dragged with the black hole, a phenomenon called frame dragging. Oh, and also another fun thing is that the singularity, the physical singularity, is a ring. Because can you understand a point particle with angular momentum in classical physics? Okay, if it's spinning, the central singularity also has to spin. But can you define in classical physics a spinning particle? It's tricky, right? So the singularity is a ring. So this is the size of the radius of the event horizon as a function of spin. So for spin equals 0, we recover the Schwarzschild radius. For maximal spin, the event horizon shrinks to half the radius of the Schwarzschild radius. And this is what I mean by frame dragging. Okay, so we can imagine if you try to build an embedding diagram for the space-time around a Kerr black hole, it's dragging space, it's dragging observers. This is what the space-time geometry looks around a Kerr black hole. Here is the frame dragging effect. The space-time around the black hole has a huge amount of rotational energy stored in space-time. And if you are smart, you can extract that rotational energy stored in the space-time around the black hole. So I like this analogy to understand what is happening around a Kerr black hole. If you go to one store, I don't know where you can buy this sort of device for your garden. If you are a millionaire and you have a huge garden, and then you can buy this kind of device here. So this is a for the distortion of space-time around a Kerr black hole. That this is a kind of embedding diagram for the geometry. Imagine you have a Kerr black hole sitting there, and imagine that in this metaphor, the water represents space. Okay, if you drag an ant here, the ant will be forced to co-rotate with the water. In this metaphor, if you drag an observer, the observer will be forced to co-rotate with the rotating space-time of the black hole. In fact, in the 60s, Roger Penrose, he thought of a smart way of using particles and destroying things around in the ergosphere of a spinning black hole to try to extract some of this rotational energy, which is a free energy, and power physical processes. This is called Penrose effect, the process of trying to extract the rotational energy of space-time of a Kerr black hole with astrophysical processes. And it turns out that the original Penrose process is not viable. It's very hard to extract this rotational energy with the original Penrose process proposed by Roger Penrose. But it turns out that you can still extract the rotational energy of the black hole with other things, which I will mention in the next lecture. Orbits of test particles are way more complicated around a Kerr black hole. Around a Schwarzschild black hole, if you throw a particle on a Schwarzschild black hole, you will always be able to define a plane. The particle will be stuck in a plane, just like the Newtonian problem, the two-body problem in the Newton's mechanics. But in the Kerr problem, this is way more complicated because the space-time has less symmetries than the Schwarzschild space-time, so orbits are more complicated. This is an example of a time-like orbit of a particle with some initial conditions. So if you were able to sustain planets around a Kerr black hole, like Christopher Nolan and Kip Thorne proposed in the Interstellar movies, I wish there was a second movie of Interstellar. The orbit of your planet will be quite tricky, quite complicated. I don't think it will be pleasant to live in a planet orbiting a Kerr black hole. Okay, the weather will be really interesting as the planet crosses several times the equator of the accretion disk. Okay, so I would not like to live in such a planet. And finally, to wrap things up about this very broad review of black holes in GR, I really love this graph, this plot cartoon made by the XKCD guy, the guy who draws the XKCD series. I don't know if you are familiar with XKCD. But this is a way of representing how extreme the gravity of a black hole is in the universe. And this is a very nice way of visualizing gravity with the potential wells. Okay, the potential wells. Here, it's not these are the potential wells of planets in the solar system. So the corresponds to the gravity of the different planets in the solar system. Here you have Mercury, Venus, Earth, Mars, Jupiter, okay, Saturn, blah, blah. Hercolubus, planet Hercolubus. There is a crazy guy here in São Paulo who goes around putting signs on everywhere about some fictitious planet called Hercolubus. I hope this is only in Brazil and not in Argentina and other neighbors, okay? So Hercolubus, the fictitious planet, is somewhere here. Okay, right. So let's imagine for fun that the height of the potential well for Earth was 1 meter, okay, so more or less 1 meter. Imagine that the gravity of Earth is such that its potential well, let's make an analogy, it's 1 meter deep, okay? And this metaphor for gravitational potentials, if the potential well for Earth was 1 meter, for Jupiter it would be 15 meters, okay? For the Sun, the potential well would be 3 kilometers, okay? 3 kilometers. 1 meter Earth, Sun, 3 kilometers. It turns out if you want to draw in the same scale the height of the potential well for a black hole, you cannot do this, okay? Because it just doesn't fit scale, okay? This is if you try to put in the same scale, you have to use log scale, okay? For a black hole, the height of the potential well would be 700, the height of the potential well for a black hole will be 700,000 kilometers, which is 2 times the distance between the Earth and the Moon, if the potential well for the Earth was 1 meter, okay? So this gives you an appreciation of how extremely relativistic is the gravity of black holes. If you are horizon of a black hole, you will be forced to be relativistic, okay? You cannot really fight this. So from now on, of course, all of you know about the Hawking radiation, that you can if you have virtual pairs of particles being popped everywhere in the universe, if you put two metal plates, you can turn these virtual pairs in real physical pairs, the Casimir effect. Turns out that this is happening near the event horizon. There is no vacuum in quantum mechanics. So near the event horizon of a black hole, you have these virtual pairs. One of the particles comes to the horizon with negative energy, the other one escapes. Okay, the one that escapes is the Hawking radiation. The one that falls decreases the area and the mass with a quantum process. This was a semi-classical calculation by Stephen Hawking in a classical Nature paper, 1973, with a very catchy title about black hole explosions in the title of the Nature paper. But the thing is, if you work out the Hawking radiation, the Hawking luminosity out of astrophysical black holes with masses bigger than about 2 solar masses, you will find out that this is, I don't remember the numbers off the top of my head, but the Hawking radiation for such a black hole is like more than 1 billion times less than a solar luminosity, or even less luminosity. I don't have the number off the top of my head. And if you compare this with the shining glow of the accretion disk around such a black hole, the Hawking radiation is completely meaningless. So for me, an astrophysicist, I don't pay attention to the Hawking radiation right now. But when we live quadrillions of years in the future, our robot overlords, okay, the heat death of the universe, Hawking radiation will be interesting. It will dictate the cosmological evolution of the universe many quadrillions of years in the future. But right now, There is no reason to really bother Hawking radiation for astrophysical black holes. So I will not mention Hawking radiation from now on in my lectures, okay? All right, quiz time. Get your cell phones, get your tablets, get your laptop, plug your AI of your minds in the Wi-Fi if you have one, if you're coming from the future. And let's do this. Very simple quiz, nothing fancy, just to have fun and see how much you know. Very simple conceptual questions. So go, in the meantime, go to this address. Okay, let's do this. They're having fun, look. Okay. Are you connected to kahoot.it? Let's do this. Please enter this code. Professors are also welcome to join this Kahoot. Okay. Ready? 3, 2, 1. Everybody in? Yes? Let's go. Whoa, 35. We have more players than yesterday. Okay. Okay, go. Are you ready? What is the main defining property of a black hole? Okay, most of you got the answer correctly. Okay, what I'm referring to is the main defining property of a black hole. Okay, very good. Kerr is in the top podium. Okay, the largest mass was 10 billion solar masses, as I just mentioned in the lecture. The maximum mass measured for a black hole. curve is in first now? Later. Ah, thank you. I should have put less question. We don't need 60 seconds to reply. Okay, it's not fundamental. Okay, so radius is really, from a theoretical point of view, the radius is derived from the other parameters. Okay. In astrophysics, charge is not really important, but in general, this one is tricky. Aha, we have an almost flat distribution. Okay. For a distant observer, he or she never really sees the star collapsing. Okay. For the moving observer, he will fall in the physical singularity, and die there, crushed by the tidal forces. Huh? Our time is. Yeah. All right. This is a tricky one. This is a tricky one. Who does not deserve? Okay, let's be clear. Let's see. Okay, very good. Somebody really likes Michel Temer here. Okay, good to know. Yeah, okay, we are done. Congratulations, Light Curve, you got the first place. Kyle, congratulations. Naturally, congratulations. I will store these results with the quiz and give a surprise prize at the end of the lectures for the top person. So please use a consistent username throughout the quizzes, okay? Because I will use this to give a prize at the end of the lectures. Okay, we can discuss the appearance of a collapsing star at the end of the lecture or in the discussion section. Let's move on now. Oops. Let's move on now and talk about the ins and outs of black hole accretion flows. And starting with the first question, what happens when you feed a black hole? What happens when you throw test particles in a black hole? We already know the answer, and Hollywood answered that to us. So here we have a fictitious black hole in some movie, okay? It was found in an abandoned spaceship. Somehow these guys are using black hole to power the energy of the spaceship. Feeding with his hand the black hole. Black hole apparently has a viscous consistency. He really wants to feed the black hole. This is what happens. No, this is not what happens when you feed a black hole. Okay, this is the crazy view of Hollywood according to this movie Event Horizon, which has terrible science, but it's a fun movie to watch. I really recommend it. So this is what happens when you feed a black hole. You feed a black hole with a cloud of gas. They usually have angular momentum. As the cloud dissipates energy due to the angular momentum, you expect to have the general formation of disks when you have material with angular momentum falling towards the central object due to the conservation of angular momentum. Okay, this is the lowest energy state of this cloud of gas as it evolves and dissipates of energy. And this is why you have disks in galaxies, you have disks around black holes, you have disks around young stars forming planets, okay? So disks are ubiquitous in the universe, and this is not different for feeding particles onto a black hole. And we can use the theory of the problem, general relativity, to understand some of the main features of a disk, a so-called accretion disk around a black hole. So thank you, Ian, for deriving this last lecture. So you can write down the effective potential for a Schwarzschild black hole, also for a Kerr black hole if you want to do that. This is how you put the problem in the framework of the effective potential, and then you plot the effective potential, and you can use celestial mechanics methods to analyze what happens. So imagine you have a disk of particles circling around the black hole. Okay, so different particles, different orbits, they have different angular momentum here. So we start putting a circular orbit in the minimum of the potential, a stable circular orbit at that point. It corresponds to this kind in the accretion disk. You go closer, you put the yellow orbit, you get closer to the black hole. You put another orbit, you get closer to the black hole, until the point where the angular momentum is so low that you don't have anymore the feature of the maximum in the potential, okay? You don't have anymore the pit in the potential feature discussed by Ian yesterday. You have the radius of the stable circular orbit, which for a Schwarzschild black hole is located at 6m. So you cannot sustain any more circular particles inside this innermost stable circular orbit around the black hole. So what happens is you expect in accretion disks around black holes that inside the innermost stable circular orbit, you will have literally a hole in the accretion disk. Part of the black hole inside the ISCO will ballistically fall onto the event horizon. So it's a hole in the accretion disk, okay? You can understand all of this with this effective potential. This is a simple concept, but it has profound implications for black hole astrophysics. Talk a little bit about black hole spin and the effect of black hole spin on accretion disks. It turns out that if you do the calculations of the event horizon and the effective potential for a Kerr black hole, the radius of the innermost stable circular orbit decreases considerably as you increase the black hole spin. In fact, for a maximally spinning black hole, the ISCO radius touches the event horizon. and co-rotates perfectly with the event horizon. This is the dependence of the radius of the photosphere, where you can have photons in circular orbits around the black hole. It decreases from 3 to the spin. And this is the radius of the event horizon of the black hole, which decreases, as I mentioned, from 2 as you increase the black hole spin. So it turns out that if you have an accretion disk around a black hole, on the left side you see the hole in the middle of the disk, or a Schwarzschild black hole. And on the right side you see the hole in the middle of the disk when you have a maximally spinning Kerr black hole. Okay. So what is the impact when you have particles in an accretion disk orbiting a maximally spinning Kerr black hole? It turns out that the disk will have access to inner orbits than the disk around a Schwarzschild black hole. So the disk will have larger velocities, it will have a larger surface area because it's going deeper in the potential, and it will be hotter because it will have higher temperatures of the gas close to the event horizon. Okay, so deep implications, as I mentioned, for observational astrophysics when you're trying to observe and measure the spin parameter of the Kerr metric. Let's now have a few words about the efficiency of energy extraction from these black hole furnaces in accretion disks. Okay, so our agenda now is that we want to derive a simple order of magnitude estimate for the efficiency of energy extraction from these gravitational engines. Okay, how can you extract blood from stone? How can you extract energy from a black hole with an accretion disk? Okay. Thank you. So it turns out that imagine you have a nice circular orbit a bit far away from the central black hole, okay, at some. So but we can even say that we can make r, the radius of the orbit, tend to infinity if we want, okay. So what is happening here, imagine that we have some physical process operating in the orbit of this particle such that it is dissipating the mechanical energy of the particle and it's making lose energy. So what happens when you start dissipating energy for the orbit of this particle around some central generic object, okay? The particle will start, depending on how fast this energy extraction is occurring, the particle will start losing gradually energy and spiraling towards the central object, okay? If you turn on some mechanism for dissipating the energy, okay? So the particle, of course, is losing orbital energy, and the actual process that dissipates this energy is turbulence. These disks are very turbulent. They are dissipating the energy on larger scales towards smaller scales, towards the Kolmogorov scale of the problem, where it is dissipated in thermal energy, okay? But I will not really talk much about turbulence because turbulence, there is a joke. I don't remember if it was Heisenberg or Feynman who said this joke, that somebody, I don't remember if it was Feynman or Heisenberg or somebody else, they asked this person, suppose you died and you wanted to ask questions, you wanted to ask 2 questions to God. What would you ask God? And then this person said, well, the first question I would like to answer is, what is turbulence? How to understand turbulence, okay? Turbulence is one of the complicated classical problems that we have. But anyway, so it's losing orbital energy. It's converting this orbital energy into thermal energy, radiated away eventually from the disk, okay? So by the time this particle fell from this radius towards potentially the event horizon the black hole, how much energy was released by the particle as it spirals inwards, okay? How much energy was lost by the particle and dissipated in the system, okay? So we can compute the amount of energy, let's call it the accretion generated energy by the particle. Let's imagine that infinity, the velocity, the distance is very small, velocity is very small, and when it touches the horizon, let's imagine that the particle stops, okay? And then we can compute the accretion, the energy released by accretion as the difference in the potential energy of the particle very far away from the central object minus the gravitational potential energy of the particle at the radius where it stops orbiting the black hole and falls into the black hole, okay? So of course, this is a simple calculation. R tends to infinity. This is not really relevant. It goes to 0. And then let's put the innermost radius where the particle falls. I will call it R dot. So let's put R dot. So this gives you an idea of the energy released by the total energy released by the particle as something dissipated its energy, okay? It's simple by this formula. G, m, the mass of the central object, the mass of the test particle, and the final radius, okay? Okay, so this is the energy released by the accretion of one particle in Newtonian mechanics, okay? What if you have a continuous, I probably mean continuous here. What if you have a continuous flow of particles towards the central object, okay? What if you have a continuous flow of particles in the sense that you are not throwing only one particle with mass m here, but instead you are throwing several particles and the injection rate of particles in your central object is dm dt, which I will call m dot, okay? You have a time derivative, you're providing particles, you are happily providing particles to the central object, okay? So in this case, what is the power, what is the luminosity of energy released by this continuous inflow of matter towards the black hole, okay? Okay, so you want to get the power release, in other words, the luminosity released by accretion, you derive this. Okay, so the only thing that is changing with time here is m, so this is the simple calculation for the luminosity released by accretion. So far, so good, right? Very simple, very easy, only Newtonian mechanics, nothing fancy. Okay. So if you remember the last lecture, okay, the last lecture we used to try to characterize the in the sense that we wrote the luminosity of the system as some inflow of rest mass energy factor, which controls what fraction of this infalling rest mass energy is converted into luminosity. So you can write the efficiency as the luminosity over m dot c square. We can write the efficiency, but we just derived from Newtonian mechanics an actual expression for an order of magnitude estimate of the luminosity released by accretion of matter. which we can just put here, and I will draw all the and see this geometrized unity. So we have here, sorry, oh no, yeah, it's correct, yeah. And we get in the end that the efficiency of energy release is simply the ratio of the mass of the central object divided by the radius where the particle stops orbiting the black hole, just falls in ballistically onto the black hole, okay? So this is, let's call this the efficiency of release of energy by accretion, okay? And it is really telling the efficiency of by accretion depends on how compact your center is. The more compact, in other words, the larger the ratio of mass over radius here, the higher the efficiency that you will have releasing by accretion, okay? So, now if we consider a Schwarzschild black hole solution as the central object, okay? For fun, let's not think about consider that the final radius of the is the Schwarzschild radius. Okay. In that case, the efficiency of release of accretion will be m over, 2m. So we will have here m over 2m. So we will have over 2, which is 50% of efficiency of energy release if you have a Schwarzschild black hole, okay? Just an order of magnitude calculation, okay? This is huge, okay? This is huge. If you are an engineer in the efficiency of this engine, you will lose your sleep getting excited with things that we will never be able to achieve with machines here on Earth, okay? The thing is that in practice, the last orbit, as we just learned, we learned yesterday and we revised today, the last orbit is dictated not by the Schwarzschild radius. The last orbit is dictated by the innermost circular orbit. That's the R dots that we should use in the formula to estimate the efficiency of energy release, okay? So the Newtonian calculation is a bit more, the GR calculation of this efficiency. And the calculation you have to do then is simply between the potential here at infinity minus the effective potential of the Schwarzschild at the ISCO, which is 6m. And do this calculation, and here, for the angular momentum of the orbit, you can derive that for the innermost stable circular orbit, the angular momentum. This is homework if you haven't done this calculation. It's a homework to derive that for the ISCO, the angular momentum of the orbit is square root of 12, okay? So when you put this here, you derive that this efficiency will actually be 1/18, which gives you around a 6% of efficiency. You can round that up to 10%, okay? So this is the efficiency of energy extraction around a Schwarzschild black hole. Okay, 6% is the efficiency of blood that you can get out of stone, the energy that you can get by dumping garbage, slowly dumping garbage into circular orbits around a Schwarzschild black hole. Okay. Now, if you do this calculation, if you repeat this calculation, I will not do the steps, but if you do this calculation for a Kerr black hole, okay, for a Kerr black hole, the Kerr black hole, the ISCO is smaller, okay, so you have larger energy. For a Kerr black hole, the calculation gives you 42% efficiency. For a not exactly a maximally spinning black hole. Hard to have maximally spinning black holes, but for the highest spin that you can conceivably achieve in astronomy, okay, due to the back reaction of photons that are accreting onto the. You can go, so you can have efficiencies ranging from 6% to 42% of extraction of energy from a black hole. So this is the actual curve of the dependency of the efficiency. How is my time going? Okay, sorry. I'm not keeping time of my. Okay. Curve of the dependency of the efficiency of release of energy by an accretion disk as a function of the spin on top, the upper axis. Okay. So you can see it going from 6% continuously up to 40%. So black hole spin, in conclusion, black hole spin, the first conclusion is the release of energy by accretion disks is one of the most efficient engines of energy extraction in the universe. Okay, number one. And number two, black hole spin leaves a considerable imprint on the accretion disk. It's faster, it's hotter, it's brighter, okay? But there is also more gravitational redshift, which will lower the luminosity of your disk at the same time for a Kerr, maximally spinning Kerr black hole. So the conclusion here is black hole accretion disks, they are the most efficient radiators of electromagnetic energy in the universe, okay? They release, in principle, only looking at these two numbers here, these two efficiencies, you can have gigantic amounts of energy, of conversion of mass into energy due to these engines, okay? Expect, in principle, to see this energy flowing in the electromagnetic spectra, somewhere in the electromagnetic spectrum. The question I will address in the next lecture, in the electromagnetic spectrum, will you see this energy being extracted from the space-time around the black hole? To give you some context here, these numbers might not look like much, okay? Between 10 to 40%, okay. Who cares, okay? But let's compare these efficiencies with typical efficiencies of processes that are important and cherished, very important and dear and close to us. So let's imagine you give 1 gram of sugar, okay, to an enzyme, okay, and it releases energy which will power your muscles, it will power your thoughts, okay. How much energy can you extract from 1 gram of sugar, okay? The efficiency of this process is 10 to the minus 11, okay? So it's a very inefficient process, okay? Our evolved biology after 14 billion years, nature evolved a highly inefficient engine of extracting chemical energy from sugar. Let's now consider a man-made machine, okay? Hydroelectric dam, like the Itaipu Dam. Okay, you give 1 gram of water into this engine, okay? Extract some of the potential energy of the water falling. How much energy can you get from 1 gram of falling water? You can very easily compute the efficiency. You get a number which is 10 to the minus 14, which is 1,000 times less efficient than our biological engines walking here and thinking, okay? You can bump this up to around 100% efficiency if water falls close to the speed of light, okay? If you have an Itaipu Dam with a height of close to the size of the solar system, I think. Now, let's consider extraction of eolic energy. You write a very simple calculation. You write the energy extracted by the kinetic energy of air. Its efficiency of 10 to the minus 14. Okay. Now you go to nuclear fusion. And what you'll see here is one of the, I think it was the largest, probably largest released nuclear test, that Tsar Bomba, which I think was 10 megatons. No, probably, I don't remember, but probably 10 megatons, okay? The efficiency of extraction of energy when you fuse nuclei to is 10 to the minus 3 more or less, okay? So this qualifies black hole engines powered by gravity as the most efficient engines in the universe for obtaining electromagnetic radiation. I think we should wrap up, Ricardo, yeah? So what are the fundamental parameters of an accreting black hole, okay? We know that one of the parameters is the mass, the second parameter is the spin, and the third parameter is the accretion rate, the rate of inflowing matter that is flowing towards the central object, which we call m dot. The m dot that I define here, okay? This is a fundamental parameter in astrophysics, okay? This is related to what some physicists call dirty physics, okay? It's not only the gravity, it's only the space-time dynamics, okay? You have to worry when you have fluids around the black hole with things about hydrodynamics, okay? Viscosity, and these kinds of things. It is a theorist's dream to compute every conceivable property of the system to give to your astronomer friends to compare with observations. It's the dream to compute every property from just these three numbers about a black hole in astrophysics, from the mass, the spin, and the accretion rate. Okay. So the next lecture, I will quickly review some concepts of fluid dynamics, talk more about accretion disks, and move on to outflows from black holes and their radiation signatures. Thank you.
Hi. You have a full supply for the mass of the black hole. Do you have something similar for the angular momentum, or is a fixed parameter in astrophysical situations?
In the accretion disk is feeding mass, and it's feeding also some amount of angular momentum, which will over time change the mass of the black hole and will change the spin of the black hole. Okay. And here I put the mass is the most important. Of course, it's very hard to reduce to only these three numbers, because when you have fluids, things get more complicated. You have, as I will talk tomorrow, the Navier-Stokes equation and turbulence and these sorts of, and magnetic fields also, which I will just barely mention because MHD, it's more complicated. So one big unsolved puzzle in black hole astrophysics is what is the final spin of black holes, okay? So LIGO is helping us to address this question, okay? Should we have maximally spinning? Do black holes in nature tend to maximally spinning black holes, or in between, or they tend to Schwarzschild spins, okay? In binary systems, this is a bit more complicated, but when you have one single clean black hole accreting mass, this is also an unsolved question, which will have cosmological implications. So in one of my lectures, I will touch on this issue of the spin evolution of supermassive black holes, and it can have dramatic impacts on the galaxies and cosmology. Okay, so this is very interesting, the connection between the micro and the macro in the cosmos. Yeah.
So sorry, just a follow-up on this, but can you relate the amount of angular momentum donated to the central black hole to the m dot? So m dot and l dot, can they be related?
Probably yes. Okay. I don't have a clean argument to give you a clean analytical argument,
you
but
can cook up an exercise for the students.
Yeah, it would be an interesting exercise, and I will mention we are now doing numerical simulations of accretion onto black holes, and for sure you can do a virtual Virtual reality, a virtual laboratory, a controlled experiment, and you can measure it in the simulation if there is a relation between the accretion rate and the angular momentum. This is a good question, actually. I'll think about it.
Analytically, you can assume it was in circular orbit, and then in circular orbit.
Oh, analytically, for sure. It's not clear to me if it's a meaningful relationship, but sure, analytically, you can do it for a simple type of accretion disk. Mm-hmm.
Hi. Can a Schwarzschild black hole become a Kerr black hole and the opposite is true?
Yes.
So
Yes. Sure. So it's, to begin with, it will be very hard to actually form a Schwarzschild black hole in nature because usually the collapsing stars, it's either a neutron star or some other more massive star, they usually have non-negligible amounts of angular momentum, okay? And it will be very hard to get rid of all this angular momentum with the thing is, astrophysics is messy, okay? Astrophysics, when you have a collapsing star, the star is losing mass, there is radiation pressure blowing away the outer layers of the star and it collapses, okay? It's usually very non-linear processes, as non sometimes as gravitational waves. So it will be very hard to form a Schwarzschild black hole from any generic collapse, okay? So usually you start with spins around 0.3, 0.2 for typical black holes. And you can either decrease that, and another way you can decrease or increase the spin is by merging black holes, okay? By merging black holes, two black holes with different orientations. The final black hole, you can play with the parameters such that the final black hole can decrease the spin, okay, depending on the mass merger. But yes, you can either turn a Schwarzschild into Kerr and vice versa, okay? With retrograde accretion, for instance, with a counter-rotating accretion, when the angular momentum of the disk, suppose this is the angular momentum of this is the angular momentum of the black hole, okay? So you can play such that you keep feeding matter with different angular momentum and decrease this spin vector of the black.
So just in the observation of LIGO, they are all broadly consistent with individual black holes, I mean original black holes having spins up to 0.2, 0.3, and the final black hole.
Point what?
0.2, 0.3, the original black holes, before the merger, and the final black hole after the merger to have spin of 0.7-ish. This is, I mean, there are large error bars, but this is the broad picture.
And 0.2, 0.3, if you use models of stellar evolution, you roughly expect 0.2, 0.3 as the initial spin for astrophysical stellar collapse, more or less.
Yeah.
So you told the Kerr black hole has a ring singularity, but to be honest, I didn't understand this. How can the singularity moves down?
How can you have a ring singularity?
Yeah.
The way I understand this is GR is a classical theory, okay? GR is a classical theory, and in classical mechanics, you cannot have point particles with angular momentum, okay? Because the moment of inertia will go to infinity, right? Schwarzschild black hole has a point part. The classical black hole. It is a point particle located at a singularity. Okay, all the mass is located at a singularity. It doesn't spin. When you start adding angular momentum to this point particle in the Kerr black hole, it doesn't have any other choice but to spread this angular momentum into a ring. Otherwise, you cannot have point particles with angular momentum in classical mechanics for that simple reason. Maybe one of the other speakers can add a bit of. Do you have anything to add?
I mean, angular momentum mass, they are measured through the. I mean, you don't measure the mass in angular momentum by putting a probe. I mean, inside the black hole, you measure the property of the space-time.
Yep.
And so, by measuring the coefficient, the 1/r fall off of the potential, you measure the mass. By measuring the torque on test particle, you measure the angular momentum. So it's really a property of the space-time.
Yeah. Yeah.
Shall I go to the next question?
Yeah, sure. But did
following that comment, since the properties are only indirectly measured, how can you be so sure that these numbers that you get are in fact or are unequivocal from a black hole?
Are unequivocal for a black hole. The
properties of the
numbers
black-
for what? The numbers for...
No, following that command, we measure things, we get numbers that we think that are coming from black holes. How can you be so sure that those numbers that we get are in fact from black holes and not already
Are you referring to the mass, the efficiency of accretion, the luminosity?
All the parameters that define a black hole.
Okay, so first of all, everything I'm doing here, I'm doing on the assumption that we can compare with observations, okay? I wouldn't do astrophysics if I couldn't measure if I couldn't compare the numbers of my theory with observations, okay? So regarding the efficiency, there are ways of estimating the energetic yield of accreting black holes from observations, okay? There are several different ways. One of the ways is, I will mention about observational signatures in the electromagnetic spectrum of black holes in the next lecture, okay? But one of the signatures that you are looking at a black hole is counterintuitively, paradoxically, very strong X-ray emission, okay? Not from the event horizon, of course, but from the accretion disk. High temperatures, high energy X-rays. What you can do in these systems, what an astronomer can do, is you make a plot of the energy spectrum, okay? Energy times the flux of energy, and then you go at the resulting spectrum, and you can actually measure the energy that is flowing out of the system, okay? And you can use the physics of GR to try to derive the accretion rate. And then you compare what you observe here with what the theory tells you if Einstein is correct. And you can have a very good idea of the efficiency of the system, okay? And things never confronted GR, okay? GR always has been able to explain the observations of these accreting black holes. We can play similar games with supermassive black holes in the centers of galaxies. We can play this game. It's more hard with gamma ray bursts. We can keep playing this game, okay? Mass, I will mention next lecture, we can measure mass with test particles far away from the black hole. We can have an idea of spins of black holes with electromagnetic observations. It's harder, but we can have an idea, okay? So everything you can constrain from observations, but as I said, astronomy is a bit dirty because you always have things which are trying to confuse observers, okay? Dust, for instance, other things. But we can, all of these can be measured, okay?
Accretion disks is essentially a lot of particles that are spiraling and falling into the black hole.
Mm-hmm.
Into the future, can we see some gravitational wave emission from these systems? Some continuous gravitational wave emission? Because we have particles spiraling and falling to the black hole.
Well, in principle, sure, there is gravitational wave emission. Okay, you have this a non-spherical accelerated system. Okay, but the thing is that the strength, the amplitude of the gravitational waves will be effectively non-observable. Okay, I don't think it will be, for the simple fact that for the typical astrophysical systems we will deal with, in X-ray binaries in the centers of galaxies, the mass, I have to compute this number, okay, from yesterday, but the mass of the accretion disk is many orders of magnitudes lower than the mass of the black hole, okay? So the accretion disk, the space-time dynamics, because of the accretion disk, is negligible, okay? Now, if you have a binary supermassive black hole, it's a different thing, okay? And also in gamma ray bursts, the accretion of matter from due to the coalescence of neutron stars is which is the accretion disk itself, because the accretion disk can be important, okay, but not for most of the systems we will deal with.
So I think that, so if the accretion disk would just be a disk, it wouldn't emit any gravitational waves. Because it's
because of the symmetry, okay.
So the thing that would, so the inhomogeneities in the disk, that would, but then of course very weak.
Yeah.
But if you would have some large chunks, then you would get.
Thank you, thank you.
Yeah, I mean,
all astrophysics. This is the dream's view of an accretion disk, but real accretion disks are inhomogeneous. Okay, they are not perfectly spherical symmetric. Okay, thank you very much.
No, it's not spherical. Even axial symmetry.
Yeah, also it's not perfect.
Symmetric
Okay.
does not emit like
Okay.
a Kerr black hole. Okay. Last question.
Well, I would like to know how the light cones look like in the ergosphere, inside the ergosphere.
Oh.
If that's possible. How's an idea? How they
I would
decide?
like to know as well. I don't know. I cannot even. Does anybody here know the light cones in the Kerr geometry for a maximally spinning black hole? I don't have a picture in my mind. Of course, the torque of the torque of the space-time will introduce will bend in certainly the spin will affect the light cones, but I don't have a picture in my mind to give you. I would like to know as well. It's a good question. I don't know.
Okay, unless there are urgent questions, I suggest to postpone further discussion to the afternoon. Now we go for lunch and we meet again at 2:30.